of the Honeybee Hive wireless environmental monitoring system, run by Tina DePina and Bradley Martin. So our customer is Dr. Fortier, and our advisor is Dr. Benjamin Weil. Dr. Fortier approached the school with an idea of trying to create a universal sensor module that could be used to accept various sensors to detect bee colony collapse. Since there isn't one exact issue as to why bees are dying, the whole idea is to accept a wide array of sensors and then distribute these sensor modules throughout a colony's area, or range foraging area. The graph on the right is from beinformed.com, very, very reputable. So the orange, the darker orange there is showing the percentage that's actually lost throughout a year, and you want to try to keep it in the yellow at a maximum. That's an acceptable loss, because you're going to lose bees throughout the winter. It's cold, insects cold don't work too well, so that's a temperature issue. Bees actually do need a decently pure water. They don't just suck water out of the air. And then there's another issue of varroa destructors. So this is a small mite that can actually attach to bees, and they mask their scent to smell like bees, and they have environmental factors that they thrive in. So trying to pinpoint something that can be a good breeding ground for varroa mites could be a good indicator if that's a warning sign for a beekeeper. So our customer requirements, this was from back and forth meeting with Dr. Fortier and then some brainstorming on our own. A major one is a minimum 30-day battery life. This is so long you can go out into the open, out in the wild, and not have an operator needing to go up to it, check data, take out an SD card or something like that. So that also brings in a wireless communication. So you have a base station, which, I mean, I'm jumping down to requirement 7, but a base station, that means an operator doesn't have to go measure data from a module, go back and forth every day. This is being transmitted constantly for those 30 days minimum battery life. Requirement 1, to jump back, was a bit vague. It was research sensors that can detect things that are affecting bee health. So temperature, water quality sensors. Up there we have a few different ones running. So we have water TDS, water ORP, dissolved oxygen, and then pH, as well as just a soil moisture sensor to kind of see if pesticides are sprayed in the area. You can kind of see what's going on just based on the moisture, but ideally that would be another pH sensor into the ground. But to kind of show the variety of sensors that can be accepted, we have 5. A 2 to 5 mile transmission range, that is the average bee colony foraging area. Ideally, they usually stay around 2, but some have gone up to 5, so we try to shoot for the longest range possible. Since these are units that are outside constantly, you don't know if it's going to rain, you don't know what's going to happen, so a weatherproof design was required. Self-health monitoring. A bit vague. Tina will talk about that more in the engineering requirements, but essentially so a module knows if something bad is going to happen. Be that low battery, overheating, something along those lines. Prevention of data loss was something that Brad had brought up to Dr. Fortier. It's kind of the onboard SD card or USB drive, something along those lines to keep it in case of a failure. If you're transmission, you lose data in between, just in case an operator can go out and grab the data off of the module. And then up to 5 sensors at a time. So on the table, which 5, you could have just one sensor if you only care about temperature, and then you could have up to 5 sensors. It doesn't matter the orientation. We'll talk more about that in engineering requirements. Base station I went over. GPS was something we added later on. If you have a network of these dispersed, and you're a different operator, so if Dr. Fortier goes out, he lays these around an area, and then he's at a different site. New operator comes in, they don't know where you put them. You're going to call Dr. Fortier? No. So GPS, you can kind of limit that up. It's accurate enough to a phone, ideally. That would be the requirement. So you can compare your Google Maps data, just type in where you are, kind of go around there, and map to where it is. And then requirement 9 was something that we kind of went back and forth, but Dr. Fortier definitely wanted, was a pump that could store, or a tank that could pump in water, store the water, detect if there were any pesticides or anything inside of the water, and determine whether or not it has to pump that water out, hold that water in case if it has contaminants, you don't want to put it back into the water. We like to hold that and see, and then alert an operator if there was a problem wirelessly.
So these are engineering requirements, and pretty much what we did is we took each customer requirement and broke them down into realistic goals that we set for ourselves. For example, so each customer requirement has one engineering requirement, but however, number 4 was broken down into 4 engineering requirements to monitor for the self-help monitoring. We have it broken down into battery life monitoring, case interior temperature, case interior humidity, and case interior moisture. Not all of these engineering requirements had, not all, they weren't. So the next slide shows more engineering requirements. So, for example, number 8, GPS. That only had one engineering requirement. Each module had to have its own GPS module in it so that we could locate the sensors after they're put out in the field. This is our functional overview. This is what was requested from Fortier. This is on the top right is a mesh network of modules that are on the 2 to 5 mile range. At the bottom is each module broken down. They have a main board and then up to 5 possible sensors connected to it. And then the main board communicates wireless to the base station, which is then connected to a computer where all the data can be read off of. This is our alternatives. We had a lot of different alternatives to look over for our project. For example, waterproofing. We looked at different ways to waterproof our system. We looked at different controllers and processors. But this is just one example. This is where we're looking at how to communicate from each sensor to the main board. We looked at our 3 options, which is I2C, SPI, and individual connectors. We try to make our system as modular as possible. So I2C and SPI connection made it very modular, so it didn't matter which sensor you connected where. Everything would work fine. However, if we wanted to do individual connectors, you couldn't connect, for example, the pH sensor to where the temperature sensor was supposed to be. So we tried to make these tables for every alternative design we had. We looked at disadvantages, advantages, prices, and how best it worked with our system.
This is what we ended up actually going with. At the top left, that's one of the main modules, so the larger board there with the antenna sticking out of it. The bottom 2 boxed ones are just to represent sensor modules, so it just says 1 and N, so up to 0 through 5, or 0 through 4, sorry. And then at the top right, that is the a slightly lower level diagram of the base station. So the base station and the main module are essentially the same circuit board. We tried to keep costs down by having the same circuit board where you can just install different components. Like the USB circuitry is on the board. If you just don't install it, then you have a main module. If you install it, then you're ready for a base station. Trying to keep costs down in production. All the sensor modules are exactly the same, but trying to show how it goes. It's a bit schematic-like, so up the top left you'll have battery and DC power in, so that's charging and battery. I mean, they connect together, but there is protection circuitry in there. DC is not going directly to batteries. Just to kind of get the idea of what's going on. And then each connector down there, that would be the same as a 0 through 4, just to minimize, but the same connectors used for every sensor, same cable. Really just trying to get modularity down. We ended up going with SPI because with I2C we would have had to address each sensor, which a couple of different ways would have been to hard program that onto each board. And then you'd have various different programs depending on what type of sensor you wanted. With SPI, we could kind of figure out what sensor it was based on what the board is doing, and then translate that data across just by saying what kind of sensor it was, and then the main module can then interpret that data. All analog to digital conversions are done on the sensor boards, and then just a raw number is sent across to the main module. And then I went over point-to-point communication. The XBs that we chose can't support a mesh network. This would just require a setup in the Digi software XCTU, where essentially just checkbox, I want to use this as a mesh. As long as all of them have the same base station address, they can work as a mesh. So this is really a proof of concept, more so than a finished product, but I would say it's pretty close.
So this is just to highlight a lot of the just main technical features of the design. Making notes a little bigger. So the main features of the main module, some of these have already been gone over. Just that it supports up to five sensors. It has GPS built in. Well, it's a GPS module that has the capability for it. It has onboard backup in the form of an SD card. It has internal temperature and monitoring, so it can detect if there's potentially hazardous conditions inside of it that can be dangerous to the electronics, like over temperature or something like that. It has ways of turning on and off the XB and GPS because those are our two highest ranked components in order to try to save battery life. And it also has the ability to have solar recharging. The sensor modules, they have rotary switches that are 16 position. This is in order to set the type of sensor that's plugged in, so you don't have to do any reprogramming. And these boards also have the same internal temperature and humidity sensor for the same reason. And the base station, it uses the same hardware as the main module, as Mike already said. And it also just, it has micro USB to again back up data and USB to send the data over to a PC. So this was just the test plan. Pretty much everything was just tested except for requirement 0, which is the battery life. This one was analysis and tested, so basically it looks like we can measure our current draw and then calculate based on the capacity of our batteries, roughly how long the system should last. And requirement 6, which was 1 to 5 sensors. This one we were able to just demonstrate. So this is our actual test results. So requirement 0, which was battery life, this test passed. We weren't able to do a full 30-day test, but we were able to do do math on the based on the current load and the battery capacity. Requirement 1 was for the sensors. This was a pass/fail. Most of our sensors are analog. We would like to see us be able to have a couple different other types of sensors besides just mainly analog sensors. Requirement 2 is 2 to 5 mile range. This was again a pass/fail. That was just because in our testing we weren't able to get the 2 to 5 mile range. However, the hardware we're using does support it. We were just using the wrong antennas. The antennas that do support that are quite expensive. Requirement 3 was to be waterproof. This test passed. We weren't able to really pass full submersion tests. It needs a little bit of water in, but that's more than enough to just be rainproof, especially if it's under the little solar panel that's over there as a little rain roof. Requirement 4 was self-health monitoring. This was a pass-fail. Right, so, sorry, the self-health monitoring, this was pass/fail. We got 3 of the 4 engineering requirements on this one. The one that tripped us up a little was the actually reporting back a battery percentage. We're kind of just reporting back we're just reporting back a voltage from the ADC. Requirement 5 was prevention of data loss. This test passed. We have the SD cards in order to back up all the data. Requirement 6 was 5 sensors at a time. This passed. We can plug in 0 sensors, we can plug in 1 sensor, you can plug all of them in, and the system still works. Requirement 7 was to have a base station. This test passed, and it's currently just running over here and just spitting all the data out to a terminal viewer. Requirement 8 was GPS. This test failed. We have the capability of it on the board. However, the GPS module we're using just exports a lot of text over serial, and it was a little too much to process in terms of memory utilization. And requirement 9 was the pumps for monitoring the water, and this was again a fail. That board and motors drew a lot of current, and they were sometimes causing our main board to reset. So this is a summary of our schedule. We broke it up into sections just so it would be easier to look at. So the communication systems, subsystems prototyped and tested. That was going to be me and Mike. We planned on that taking 35 hours, and it actually took 113. Waterproof designed and tested, that was Mike. That was planned on 3, it was actually 10. The sensor subsystems complete and tested was all 3 of us. We planned on that taking 36 hours, and that took 89. The board design is complete, ordered, and built. That was going to be me and Mike, and that we planned on 55, and it ended up being 70. And all of the programming, which would be all of us, and we planned on 65, and we went a little over 70. So, not all of our requirements were met, but most of them were. We have most of the hardware capabilities in order to meet all of them. But more testing is required. We went a little over on our budget. This budget of $500 was also based on the fact that we're going to be reusing sensors from previous years. We didn't have access to these sensors, so a fair amount of that budget just went to repurchasing sensors. And just some of our major drawbacks are there's occasionally a data loss over the SPI communication between the main module and the sensor modules. We believe this to be just a slight programming issue. SD cards sometimes fail to mount to the board, and when this happens, the SD card has to be reformatted on a PC. And also the 5-volt rail on our main board will sometimes lock up, and you just need to reset the board by repowering it.
So when we came in, we started, we had tests running since we came in at roughly 7:30. So every minute and a half, we're writing data to the SD card, and then that SD card is grabbing data off, sending it wirelessly from there, over here. It's not a crazy range, but we can show it live, So Brad was grabbing the SD card off of the screen so we can kind of show you the data. It's over here on the screen. I can show any of the judges if they'd like to see. Just lines of text. It's mainly meant to import it to Excel so you can graph stuff over time, just to see what's going on in an area. So as soon as he grabs that, we can open up and talk about data.
What are your sensor types?
So currently, what's in there right now, we have a TDS sensor. From left to right, I might be mistaken from seeing it, but it should be TDS, pH sensor, soil moisture sensor. Oh, sorry, in the pH one, there's also a dissolved oxygen sensor. And then that orange one all the way to the right is water ORP sensors. They're all looking at different things. It's pH, relative pH. ORP is oxidation reduction potential. So that's how well water can absorb oxygen and how good that is for, you need oxygen and water for, I mean, that's more of a fish thing, I guess, than a bee thing, but that's our current loadout for that module.
Dust as well?
On the setup right now, no. For what's being demonstrated, it's just those 5. We kept the pump out to talk about that more, actually. The pump failed in a sense that we didn't trust it enough to keep it on the board, as it would take about 15 seconds. I believe the capacitors and the inductors on the regulator that we chose an off-the-shelf regulator for that, just because we thought it'd be easier instead of the custom ones we have on there. So that's just a range of 2.5 to 5 volts, and it can convert it up to 12 on that range. So we figured no matter what the battery is, we can handle that, because the battery is 3.7, fully charged around 4.2, and we're calling it dead at 3, which, based on the capacity rating, we're getting about 97.49 at 3 volts, calling it dead. So that's where we're keeping that. So that's really the main reason the pump failed, is I don't trust it enough. Yeah.
You originally represented this as a Honeybee beehive monitoring system, but it looks like what you really have is a low-cost, remote data, unattended data acquisition system for perhaps all kinds of environmental applications. Did you folks research the potential customers for such a device?
So, I mean, the main one was honeybees, just because we want to grab data as much as we can. We looked into, not competitors, but similar products. The company name is Liberium, I believe. They make a similar setup, about $1,000 per sensor setup. I think that's 3 sensors. And they have it set up where, similar to what you would want. So they have an agricultural where you can throw it in. I believe it's meant for a greenhouse. So based on what we have, we can support, with the same module, up to 16 different types of sensors. So depending on what you want, you could just change that out. It could be reprogrammed to be whatever you want, essentially.
Well, it seems with the focus today on climate change and environmental issues that there would be all kinds of particularly non-profit organizations interested in monitoring things like reservoirs, for example. And such a device might be very useful where they don't have the government's money to go out and buy a $10,000 system, but a $500 or a $1,000 system that can record data for 30 days and transmit a couple, 3 or 4 or 5 miles away could be very appealing. This could have application in many different markets.
Yeah, even with just the point-to-point, I agree with that. Especially with mesh integration, you can lay these around a whole area and gather data points from there. So there's
Even
that.
the military might be useful.
Is there any other questions while Mike is pulling up the data?
So how do you communicate with the place? You said that it's got some type of main network over there or something, right?
So from main module to base station, it's XBs. From sensors, from all the sensor nodes to the actual main module, it's SPI.
And so on to that point, so have you looked into the vulnerabilities of this type of communication network? Or like how easy would it be for me to be able to just connect to this network and be able to get data or manipulate it for anything I want to do? If this was an application that was actually being used.
That was a little out of the scope of what we were trying to focus on. That is something that would obviously be a bigger risk if this was to be rolled out right now. So to answer your question, no, we didn't really look into that all too much.
I really don't.
That's test demo. Pretty sure we very clear about. You know, it's demo.
So test demo and then you can. Hang on.
Did you, so you mentioned on the SCI, you use that connection sometime, figure out exactly what kind of software?
Not really a connection. It's not really a connection loss per se. It's occasionally we get a bit shifted to the left or right. It was only every now and then with a particular sensor. One of the sensors we have up there, I think it was bad. It's producing data most of the time, but having it fail at all, we just wanted to mark it as bad. We don't know why it's shifting a bit to the left or right, because you'll change like a 30 to a 60, something like that. You don't want that. I mean, right now we have an idea of 100 reads a day, so 100 scans a day, and then one big transmission at the end. Definitely with the power to increase battery life. That can be edited. That's easy enough to change. Like, it's just defined at the top of the code. Not easy for someone that doesn't know code. You can't just type in how often you want to do these things, but it's simple enough for someone that knows a little bit of C programming. So from 751, we had restarted it just to make sure it was working. So from left to right, we have date, time, sensor module number. So this would be beneficial for when being in a mesh. The sensor would know, so you kind of know which module number you're looking at. And then you can input the type of hive you're looking at. Around here, it's mostly Italian honeybees, I believe, just because they're a lot more gentle than like African honeybees. So if you're looking at different types of bees, you can change what you're looking at to try to keep that data more organized. This right here, this 195, that's a battery voltage. So this would be 195 out of 256 on the voltage to ECE. Oh yeah, and it's draining as it works. So it's slightly, but. And then you have sensor type. This one is a sensor type. It's labeling 0, and then sensor type and sensor type. And then these last ones are temperature and humidity on inside the case. So that can be reported back if you see a humidity of 100, you know something's really bad. So this isn't changing a lot, but you could just graph temperature, I guess. Ideally, we do this with Excel, but I don't have Excel on my laptop. So, not a very eventful demo, but there's numbers that mean things.